Okay, our project is a thermal overload relay using LabVIEW. I am connected I have taken a machine in single phase induction motor. The single phase induction motor is connected to LabVIEW through this DAC. This is DAC USB 6009, and I used a CT here to read the actual motor current by LabVIEW through this CT and the DAC. Actual motor current is going to be read from the direct front panel itself. I am going to measure the current, and we can see the black diagram here. From the DAC we are going to obtain the actual motor current. That motor current is going to be squared, I square, and that I square is going to be multiplied with R, which is result nothing but the copper loss I square R, which is the main component responsible for the temperature rise in electrical machine. That I square component is in watts, so that is going to be multiplied by the K. K is actually the machine temperature rise constant. As we gradually load the machine, how the temperature is going to rise. That curve, the slope is that nothing but this K value. K units are per degree centigrade per kilowatt per second. Even temperature is also a function of time. That's why these units are in per degree centigrade per kilowatt per second. I am going to multiply this watts, which is actual component of heat, is going to multiply with this K, which is in units per degree centigrade per kilowatt second. The entire product will give us just degree centigrade, which is the actual temperature. Here all the signal represent the temperature signal in terms of voltage. So here I am going to add the initial room temperature T0. T0 is nothing but our actual normal room temperature. There somehow like 26 degrees centigrade or 27 degrees centigrade. I am going to add this initial room temperature to the actual winding temperature. Here the capital T is nothing but the actual safe value of working temperature for the motor. Here the motor safe working temperature is given as ambient temperature as 40 degrees centigrade. So I kept the safe limit as 40 degrees centigrade. Now you can see this is the actual motor resistance, this is the K value, and this is initial temperature, which is at room temperature. This is the safe value for which we have to protect the motor. Okay, that I continuously monitoring that current, and the actual value of temperature is going to be monitored here on front panel. That is going to be compared with the actual safe value of temperature. As I already told you, the safe value of temperature is 40 degrees centigrade. Actual operating temperature is going to compare with this 40 degrees centigrade. Whenever the operating temperature is more than the safe limit, the relay is going to be tripled and the motor is going to be shut down. That is how our project is going to work. ఇంకా స్టార్ట్ చేయండి. Now I started the motor. Okay, this is front panel of our project in LabVIEW. You can see here current rating is gaining so rapidly. This is because of we all know that AC machines have their own initial inrush currents. At the time of starting they draw enormous amount of current. We can see the value here. Even here also the current is showing as 1.4 even at the starting. Very high value of current even at the starting without any load. You can see even it is going more and more. 3.46. It is still growing. Yes, initial inrush current is gradually suppressing. It is coming down. Initial inrush current coming down now. You can see here initial inrush currents are coming down. They gone up to peak value of 2.6 amperes, and then they come down to 0.6 amperes. This is what actually happens with the AC machines, even almost electrical machines. Those kind of initial inrush currents are always there. That's why we use starters and all to protect the machine, to avoid such kind of initial inrush currents. I am gradually applying voltage. I am gradually increasing the applied voltage to the motor. Yes. Now you can see this is the actual value of time. Now you can see whatever the reading here shown in panel, we can all see the same reading on our front panel. That is how the CT works actually. We can see this is the actual value of operating current of our motor. Same thing on the front panel also. I am slowly increasing the current. I set the temperature limit as 40 degrees centigrade. If the operating temperature goes beyond this 40 degrees centigrade, the machine is going to trip. I am slowly increasing the current. It is 3.2 amperes, 3.5. Actually, this machine rated current is up to 7.5 amperes. I will load up to 5 amperes. Current is increasing gradually. Now we can see even I loaded up to almost 5 amperes, but now the actual value of operating temperature is 32 degrees centigrade, but our limit is 40 degrees centigrade. You can see this, it is slowly increasing. Very slow, because temperature is a real physical signal, which is not going to increase as rapidly as possible. It's going to increase gradually. You can see the rise in temperature. Yes, now the temperature is 34. It takes some time for the winding to heat it up. In actual operation, whenever fault occurs, it will have enormous amount of current that will rapidly rise the operating temperature of the machine. Even at that conditions, this is going to shut down the motor automatically, so that the operator in the control room knows that there is some kind of fault because of which our motor is tripped, and the indicator shows that relay has been tripped because of overload. And the operator will come to the motor and resolve the problem. Motor put change Now the motor is working with its rated, of course less than rated, but rated speed and all rated conditions. Very close to rated conditions. Very close. That is what actually our mission we take in this project, that is single phase induction motor. Yeah, now the operating temperature is 37, very close to 40, but it takes time to rise to the 40 degrees centigrade. Yes, it is now 38. We can see head